Hello dear student, myself Prof. Sabburij. Today we learn new topic, first law of thermodynamics. Last lecture we can discuss introductory part in a thermodynamics. We firstly discuss what I mean by thermodynamics. Actual definition of a thermodynamics. Thermodynamics is the branch of the physics that deals with the concept of heat and temperature and the interconversion of a heat and other form of a energy. Today we discuss here first law of a thermodynamics. What is a statement of a first law of a thermodynamics? Firstly, we discuss here the first law of thermodynamics gives a mathematical relation between heat and work. This first law of thermodynamics gives a mathematical relation between heat and work. We firstly discuss here positive work done by a system with neat label diagram, and then we discuss negative work done by a system with a neat label diagram. Firstly, we discuss here positive work done by the system with neat label diagram. Positive work done by system with a neat label diagram. See this diagram. See this diagram. Consider an ideal gas enclosed in a cylinder. With a movable, massless, and frictionless piston, as shown these figures. This is a movable pistons. Consider here. In this case, the gas inside the cylinder is considered as a system. And the cylinder along with the piston is considered to be environments. This is considered as a system and this considered as a environments. Assume that the gas is expanding. During expansion, the gas molecule which strike the piston and transfer their momentum to its and exert pressure on it. That time what happened? As the result, the pistons move through the finite distance. Therefore, during expansion, the gas does not a positive work on the pistons. Some question asked on this topic. Explain positive work done by a system with a neat label diagram. Then we consider another points. Negative work done by a system with a neat label diagram. See this diagram. Consider an ideal gas enclosed in a cylinder with a movable, massless and frictionless pistons as shown these figures. In this case, the gas inside the cylinder is considered as a system. Same way, the gas inside the cylinder is considered as a system and the cylinder along with the piston is considered to be the environments. This is the environments. When the piston is pushed in so that the volume of the gas decreases, the gas molecule decreases, the gas molecule strike the piston, gain momentum from the pistons. As a result, the negative work is done by the gas on the piston during a compression. Then question asked on this topic, explain negative work done by a system with a neat label diagram. Okay, we firstly discuss here uh, positive work done by a system, and another one we consider here negative work done by a system. Then next point we can discuss here, next point we can discuss here the expression for the amount of work done in a changing the volume of a system. The expression for the amount of work done in changing the volume of a system. Consider a closed consider system is enclosed in a cylinder. In a cylinder with a movable pistonless, massless and frictionless piston so that its volume can change. This is the pistons. Let the cross section area of this cylinder, cross sectional area of this cylinder, and the pistons, consider this cross sectional area capital A, and the constant pressure exerted by the cylinders, or a system on a piston be the P. Then we calculate the total force exerted by the system on the pistons will be F is equal to PA. This is a total force exerted by the piston, exerted by the system on the pistons. F is equal to PA. We can write in this way. This is the total force exerted by the system on the pistons will be F is equal to PA. Here P is a pressure exerted on pistons and capital A be the cross-sectional area of the cylinders. Then if the pistons move through an infinitesimal, if the pistons move through an infinitesimal, that is we consider very small, this distance we consider here delta x, then the work done by this force is dw is equal to pa into dx. Consider equation second here. But the infinitesimal change in the volume of the cylinder dv is equal to a into dx. Consider equation star here. Hence the work done by the system in bringing out this infinitesimal change in the volume can be written as, we can write this dw is equal to p into dv, because dv is equal to a into dx, and consider equation number third here. If the initial volume of the cylinder is V suffix I and its volume after work done or some finite change in the volume this volume consider here V suffix F. Then the total work done in a changing volume of the cylinder is given by W is equal to integration changes V suffix I to V suffix F P into dV. We can write W is equal to integration changes V suffix I to V suffix F P into dV. Uh, Put the initial and final value in this equation. We get P is equal to V suffix F minus V suffix I, gives equation number 4. Equation number 4 here. As the internal energy of a system can be changed by doing work on it or extracting work from it, equation 4 gives the amount of work done in the changing the volume of a system. Question asked on this topic is derive the expression for the amount of work done in changing the volume of a system. Then we discuss next point here, the equation for the first law of a thermodynamics. Equation for the first law of a thermodynamics. We can calculate or derive equation for first law of a thermodynamics. When the amount of heat, suppose this heat, consider here Q, is added to the system and the system does not do any work during the process, its internal energy increases. The amount, suppose this internal energy becomes delta U is equal to Q. Another case, when the system does some work to increase its volume and no heat is added to it, while expanding the system loss energy to its surrounding and its internal energy decreases. In that time you can write delta U is equal to minus W. As the internal energy can be changed using both the way, we can consider the total charge in the internal energy as we can write this total change in the internal energy. We can write here delta U is equal to Q minus W. Consider equation first, and this equation first gives the mathematical statement of the first law of a thermodynamics. This is a mathematical statement of a thermodynamics. According to the equation first, the change in the internal energy of a system in a difference between the heat supplied to the system and the work done by the system on its surrounding. We can rearrange equation first. Rearranging equation first, we can write another way. Q is equal to delta U. Q is equal to delta U plus W. Consider equation second. This equation second also represent the first law of a thermodynamics. Q is equal to delta U plus W, and actual statement of a first law of a thermodynamics we can written here. What is the actual statement of a first law of a thermodynamics? When the amount of heat Q is added to a system, its internal energy is increased by an amount delta U, and the remaining is lost in the form of work done W on the surrounding. This is a actual statement of a first law of a thermodynamics. In this topic, ask some question. Deduce the equation for the first law of a thermodynamics and write both the form of a both the form of the law. Then we discuss some question on this topic. Another question. First question is first question. A resistor held in running water carries electric current. Treat the resistor as the system. A resistor held in running water carries electric current. Treat the resistor as a system. First question, does heat flow into the resistors? Answer is no heat flow into the resistor. Next question, is there is a flow of a heat into the water? Is there is a flow of heat into a water? If the resistor is heated due to the Joule's heating effects, then it would transfer heat to the waters. Next question, is any work done? As there is no mention of a change in a volume, therefore no work is done. And another question is, assuming the state of resistance to remain unchanged, apply the first law of a thermodynamic to this process. For the resistor, transfer of a heat into the water without any work done implies that Q is negative. Hence, according to first law of thermodynamics, we can write the equation delta U is equal to Q minus W. Therefore, dW here delta U is equal to minus Q. And last topic, we can compare here. Compare the condition for positive, negative and zero internal energy. This internal energy is denoted by delta U. Firstly, we consider here schematic representation and then relation between Q and W here. See here, uh, this is a positive internal energy, positive internal energy delta U greater than 0. We consider here Q is equal to 2000 joules or 200 joules and W is equal to 100 joules. This system, according to first law of thermodynamics, delta U is equal to Q minus W. We consider Q is equal to 200 joule and W is equal to 100. We get delta U is equal to here plus 100 joule, that is a positive internal energy, and according to this, more heat is added than the work done by the system Q greater than W. Another case, negative, that is negative internal energy, that is delta U less than 0. Here Q is equal to minus 200 joules, and W is equal to minus 100 joules. Consider this system. The internal energy become here delta U is equal to Q minus W. Q is equal to minus 200 joules, and W is equal to minus 100 joules. Then we can calculate delta U. Here minus 200 joule plus 100 joule, this become minus 100 joule. We can write here, more work done is done, more work done is done by the heat added to it. Heat added to it. Here we can write Q less than W. Then here consider negative internal energy. And last one, zero internal energy, that is delta U is equal to 0. We consider here Q is equal to 200 joules, and W is equal to W is equal to 200 joule. Then system delta U is equal to Q according to uh, first law of thermodynamics. Delta U is equal to Q minus W. Then 200 minus 200, this becomes 0. Hence heat added to system and work done are the same, that is Q is equal to W. In this way, we compare the condition for positive, negative, and zero internal energy. In positive internal energy, more heat is added than the work done by the system. That condition is Q always greater than W. And in negative internal energy, here delta U less than 0, then more work is done by the heat added to it. Then Q less than W. And last case, internal energy 0, that is delta U is equal to 0. Then heat added to the system and work done are the same, that is Q is equal to W. In this way we complete this point. Firstly, we discuss here positive work done by system with neat label diagram. Another one, consider here negative work done by system with neat label diagram. And last one, we can derive expression for the amount of work done in changing the volume of a system. Then we can discuss the equation for first law of thermodynamics. This delta U is equal to Q minus omega, and Q is equal to delta U plus W, not omega, W. This is a mathematical expression for the first law of thermodynamics. And last point we can discuss here, compare the condition for positive, negative, and zero internal energy. Today we stop here. Thank you.